and selectivity factors. So K sub R and alpha, and how those are related to one another. The retention factor, again, tells us a little bit about how well a particular analyte is retained, right? Retention factor. The selectivity factor tells us more about how two different analytes are separated on a column, right? How well can we separate two things? Remember, selectivity is about being able to differentiate between multiple components in a solution, in a compound, in a mixture. And so we often think about how well things are separated in resolution, right? And we also have resolution when we talk about liquid chromatography. And so in each of these examples, these two peaks are here at the top. They're not very well separated. They get a little more separated, and here they're very separated. When we discuss resolution, it's a way for us to, like we discussed in mass spec and in UV vis and IR and all this kind of stuff. It's a way for us to, how well are we separating these two peaks? It's a little bit different in chromatography than it is in mass spec or NMR or something like that, because instead of taking a particular peak and making it more narrow, that's what we do in UV vis, that's what we do in IR, we try to narrow things up so we can see what's around it. In separations, that is an option, but that's a much more difficult option than just taking those two peaks and separating those two peaks in time, right? Because we're separating based on time rather than based on wavelength or mass or something like that, it's much easier to separate in time than it is to actually change that peak shape. Okay, and so there's a couple ways to think about resolution, but the most common is to take something called the full width at the half maximum, FWHM, full width at half max. That's what this line here is indicating. At half that peak height, we're going to take the whole width of our peak, right? And that is one way of looking at it. Another way is looking at the baseline width, right? Because our textbook uses baseline width, that's the one we'll stick with, just so that we're not confusing ourselves. Okay. And so to calculate resolution R, we take the difference in the retention times. So TR2, let's say, minus TR1. And we're going to divide that by the average baseline resolution. So 1/2 times the width at the baseline for component 1 plus the width at the baseline for component 2. In a separation like this, the reason that we try to get good resolution, right? Not only do we want to tell what all our peaks are, but remember that the whole point of chromatography is not an analytical method, right? It's a separation method. And in order to get these compounds isolated enough that we're sure that we're getting all of that particular compound and not any mixture, right? It doesn't have to be super separated like this, right? If we look at this bottom option, right, this is separated very well. We have no problems with this resolution. But if we think about it, we're kind of wasting a little bit of time, right? This time with no signal is time that could be spent doing other things. Here in this top one, we have this pretty significant overlap of these two. And so for, let me erase that. You know, if here's where one starts and here's where the other starts, all of this time is really a mixture, right? And we don't want mixtures. That's the whole point of this. We're trying to separate things apart. Here, in this one, we still have a little bit of mixture, right? But it's much less. Here we have no mixture, but we're kind of, you know, wasting a little bit of time. And so they've calculated these R values here on this particular example. So 0.7, a lot of overlap still, 0.1 or 1 even, you know, we still get a tiny bit of overlap. 2.2, we're down to the baseline and then some, okay? And so for us to consider things sort of analytically resolved, we want R to be greater than or equal to 1.5. To be considered resolved, okay? Now, I'm not saying that this resolution at the bottom of 2.2, you know, we could be doing so much better if it were only closer to 1.5. That's not what I mean, right? But if we have one peak and then we wait 5 minutes and there's another peak, well, we could probably shorten our separation by changing something and save ourselves, especially if we're running, you know, 100 environmental samples. If I can cut 4 minutes off of each sample, I'm going to save myself 6.5 hours, right? So when we look at a resolution, when we calculate resolution, we're going to use an R of greater than or equal to 1.5 to consider our peaks fully resolved. And so that's sort of the balance between, you know, full separation where we know that we get all A and all B and no mixture, but also balancing the fact that we don't want to spend a whole lot of time doing it. Okay. We talked first thing on Wednesday about plates and how when we talk about chromatography, we talk about these individual plates in a physical column that sort of only exist in theory in a chromatography column or even in a distillation head. And so column efficiency is given by this theoretical plate height, this number of theoretical plates. And so you'll see this abbreviation, and what this means is height equivalent theoretical plates. Again, these plates don't exist, but because our column is a certain length, you know, we have theoretical plates where this separation can occur, and we want to know, you know, what the height equivalent of those theoretical plates is. So when we look at, so the number of theoretical plates, if we increase the number of plates, we increase our resolution, we increase our separating power, we increase our column efficiency, right? All those things tied together. But also when we increase the number of plates, we're not actually changing anything in our instrument, right? So the length of our HPLC column stays fixed at 15 centimeters or 25 centimeters or whatever it is. And so if we increase our plate height by altering some other things, what we're doing, or sorry, if we increase the number of plates by altering some other factors, then we're actually decreasing the height of that plate, right? And so the number of plates is equal to the length of our column divided by the height of the plate. And so in here is the number of plates. L is the column length. And then height is, sorry, height is the HETP that I talked about earlier. The reason I giggled a little bit is because I was thinking, you know, when we discuss column lengths, you say there's 10,000 columns in a 25 centimeter, 10,000 plates in a 25 centimeter column. You know, you're not necessarily going to give that column height in centimeters. You're going to change it to micrometers or whatever. And it made me think about one of the questions that we had. You know, if you wanted to increase signal to noise, you need to add a certain number of scans. How long would that take? And I told you to not give me a number like 8 million seconds. And so, God love you, about half of you converted it to kiloseconds. I was expecting hours, maybe minutes, but y'all converted it to kiloseconds. Like, how is that any easier than seconds? Mercy. At least you keep it interesting. So this column length, we could give it in centimeters, but more often than not, we're going to convert it down to something that's a more reasonable value. And so lots of columns have, you know, somewhere around 10,000 plates in a column. Now, because these are theoretical columns, they don't actually have a height and they don't actually have a number. So how in the world do we figure this out, right? This is all theoretical. So the way that we have sort of come up with calculating the height of these theoretical plates is using the actual chromatogram. And so we end up with the number of theoretical plates is equal to 16 times the retention time of a particular peak divided by that peak's baseline width squared. Okay. The textbook goes through a little bit of that derivation, but that's the important bit of it, right? And so what this means is that for each peak, we'll have a different number of theoretical plates, right? And really all that means is that for one compound, our column's really good at slowing it down. And for another compound, it's not as good at slowing it down, right? But we want that because we want it to be different for different compounds. And so this number will be different for different peaks in our chromatogram. Okay. But then, of course, if you know the length of the column, you can figure out the plate height from that. Okay. All right. If I go back a slide or two, when we talked about resolution, I talked about the difference between this full width at the half maximum and the width at the baseline. The reason that in chromatography we sometimes use this full width half max is that baseline can sometimes get a little wonky, right? Those of you that did GC over the summer, maybe you saw that baseline sort of increased over time, or you saw that those peaks were not even and that one edge of that peak sort of drifted out a little bit. And so the baseline width of our peak, you know, is not always the easiest thing to look at. And so for the number of theoretical plates, we can also look at this in terms of the full width at the half max, and it's equal to 5.54. Again, our textbook goes into a little bit of this derivation, times the retention time over this full width half max squared. Again, just as a sort of a visual demonstration, if we have a nice symmetric peak, then there's no problem using the baseline width. If we have a phenomenon called tailing, the tail of our peak is a bit longer than the front of our peak. And this is no bueno, right? This is, you can tell that the peak really should be here-ish, right? But it's not for some reason. And so using that baseline width, it's probably going to mess us up. But if we use the full width at the half max, right, it's going to be much closer to what it should actually be than that baseline width. Okay. The other concern that we sometimes have is that if your baseline is drifting, and it could be that it looks like that, right, and it doesn't come all the way back down to the baseline, and if this is your baseline. Or one last example, if you're not very well resolved, you know, what's the baseline width for that first peak versus that second peak, right? These are all concerns. What are you giggling at? So all of these are reasons why sometimes it's easier to use full width half max in chromatography than baseline width. Okay. All right. Another way that we look at the efficiency of a column and the efficiency of a separation, and really these factors that lead to peak broadening. So remember I told you we could either separate it in space, and we'll talk in a minute how we do that, or we can actually change that peak shape. And generally speaking, it's easier to separate things in space in chromatography than it is to change the peak shape. But this Van Deemter equation tells us a little bit about what affects that peak shape. And so the Van Deemter equation is related to the height of our theoretical plate. Right? And it's a pretty generic looking equation. A plus B divided by V plus C times V. Again, H is our theoretical plate height. A is this factor that takes into account eddy diffusion. Okay. B is a factor that takes into account longitudinal diffusion. And C is a factor that takes into account the rate constant for our solute going in and out of the mobile phase. Sorry, our solute going in and out of the mobile phase. And so this is a mass transfer rate constant. V here is the linear flow rate, the linear velocity of our mobile phase. Okay. So in order to, do we want plate height to be large or small?
Large.
I don't think Annabelle agrees with you. Annabelle says small. So we want the number of plates to be large because we want to have a whole heck of a lot of separation in our column. If we need a large number of plates, then each one needs to be real tiny. Right? And so we want a very small plate height. And so we want to minimize each of these terms And so this eddy coefficient, we want to be small. B over V, we want to be small. And C, we want to be small, right? The velocity, that one gets tricky. If it's small, then our B term gets large. And if it's large, then our C term gets large, right? And so this one, this is what we have to balance, right? Since I made these slides, I don't really remember what's on the next one. Not what I want, but that's okay. So looking at each of these components, the eddy diffusion, this is, if we have our column, here's my column, right? In HPLC, a column is filled with packed beads, right? We talked about this a little bit in 214. Do you remember? I don't know if I don't remember how much we talked about it in the spring with everything going on, but in 2 years ago, we talked about it. It could be that our analyte A travels through here and takes a fairly straight path, right? It could also be, however, that a different molecule of A manages to do this and takes a much longer path, right? You can imagine that the first molecules that come out of our that elute off the column are going to be the ones that take the straightest path. The last molecules of A that elute off the column are going to be the ones that take the craziest path. And so, you know, the extent to which this eddy diffusion occurs is that A coefficient. Okay. This is going to have a lot to do with how well the column is packed. It has to do with the size of the actual packing material, the size of the beads. And so this is a property of the column. And so we can reduce A with smaller packing, smaller beads. That are well packed. Okay. If they're sort of loosely packed in there, things are more likely to find these odd paths through them, rather than if they're very tightly packed, they're going to go in pretty much a straight line.
This reminds me of that game on Wheel of Fortune where they have to like drop the disc.
Go?
Yeah.
Price is Right, not Wheel of Fortune.
Price is Right. Sorry. I get those two mixed up. Price is Right. Yeah,
sort of. So, you know, the one we want is the very boring Plinko right down the middle. The one we don't want is the more exciting Plinko. Where's it gonna go? Where's it gonna go? But we can reduce that by having a smaller number of beads and those beads being very well packed. Imagine if instead of staggered, those Plinko pegs were all in straight lines. your Plinko thing would go straight down. That's really what we want.
Yeah, that is what we want.
Okay. B is the longitudinal coefficient. And this has, so remember I told you when we talked about gas chromatography that that needle injects it super quickly because we want as small a volume as possible on the column, right? And so for this longitudinal coefficient, say that this is our volume of our analyte, right, as it enters the column. As it moves through the column, it's just going to happen that those things spread out a little bit just due to the nature of diffusion. This one I kind of equate to 5-year-olds at the zoo, right? If you just sort of let them go, they're going to spread out all over creation, right? You got to have a couple chaperones there kind of herding them along if you want them to stay in a group. And so this is why it goes like 1 over v. The higher the velocity, the better they stay together, right? The higher the velocity, the less opportunity they have to diffuse out. And so if you keep them moving, then they're going to stay in that group, and that B term is going to be small. But if you slow that velocity down, they're going to have more opportunity to wander apart, and they're going to make for a broader peak. Right? You can imagine that if they stayed close together, you'd have a peak that looked kind of like this. Where's a peak that looked kind of like this? Where's a peak that looked kind of like this? Right? We want very narrow peaks when we can get them. And so we want a velocity high enough that it's going to minimize that longitudinal diffusion. Okay. This mass transfer piece, this last piece here, has to do with the fact that as our stationary phase, our stationary phase doesn't move, but our mobile phase does, right? And so so let me draw sort of some stationary phases here. Stationary phase, stationary phase. Here's our analytes. There's an analyte on the stationary phase. There's an analyte on the stationary phase. If we're moving along, the mobile phase is moving along. Right? What's going to happen is that the stuff that's in the mobile phase is going to, well, keep on moving. Right? The stuff that's in the stationary phase is going to get sort of left behind. Right? And so you get this separation. As the mobile phase moves, it pulls the analyte that's in the mobile phase with it. And the stuff that's set on the stationary phase has to, do its KD. It has to do its distribution constant before it can leave the stationary phase and go back into the mobile phase and join up with everybody else. And so you can imagine that if what's in the mobile phase is moving, and then we have to wait for what's in the stationary phase, we're going to broaden our peak, right? And so peak broadens if mobile phase moves too fast for analyte to reach equilibrium with that stationary phase. Okay. What we want is that it has enough time that it is interacting with that stationary phase and doing a good separation, and then we just move it along to the next little bit of stationary phase. That way we sort of keep all of our molecules together. Right? We can also think about this as kids at a zoo, except you've only got 5% of your kids are interested in the iguana, and everybody else wants to go see the alligator. And so the alligator kids move forward, but those iguana kids, they're stuck at the iguana, right? And then and then the alligator kids are stuck, and the iguana kids move on to the frogs, and you separate out this group based on their interests. Here, you're separating out your analyte based on how well they interact with that stationary phase. You want to go slow enough that everybody gets to see all the exhibits, and then you keep your group together. And so that's why for C, we want a low velocity so that everybody gets to see everything. For B, we want a high velocity so that they just don't run amok and we can keep them all together. And so if we graph the Van Deemter equation, so this is going to be V, this is going to be plate height. We end up with a curve that looks, it doesn't go up quite that much. We end up with a curve that looks kind of like this. Okay? And there's some range of velocities that's actually pretty good and gives us sort of our lowest possible plate height. This being said, this is why it's sometimes difficult for us to really change the width of our peaks, right? Changing A requires changing the column we're using. Right? Changing B and C terms require changing the velocity, but likely we're already somewhere in this minimum. And if we go lower, we're going to increase it due to the B term. If we go slower, if we go faster, we're going to increase it due to the C term. And so it's difficult for us to really change the width of our peaks. Right? And so for us to get good resolution, we need to be able to separate the actual peaks from one another in time. And we do that by changing what the mobile phase is, right? Changing the stationary phase requires changing the column itself. But changing the mobile phase is just switching over a solvent. Okay. So iso, prefix meaning?
Same.
The same, right? So this isocratic, right, uses the same solvent, the same mobile phase throughout. Kiloseconds. I still can't believe that. Gradient dilution is where we're going to slowly change that mobile phase over time. So let's say that we have a nonpolar column, a nonpolar stationary phase. Okay? What's going to stick to that really well? Polar analytes or nonpolar analytes?
Non-polar.
For sure. And so I'm going to write those analytes in the same color. There they are. Blah, blah, blah. And our polar analytes, they're up here. Oops, that was a P. Right. And so that's, if we have just one polar mobile phase, what's going to happen is that, you know what I'm going to do? I'm going to change these A's to B's so it matches our picture. So our polar mobile phase is going to pull that A off pretty quickly because he doesn't interact a whole lot with the column, right? And so that A peak shows up early. Okay? But then the B, because it's still a polar solvent and a pretty non-polar analyte, he's got to be polar enough that he dissolves in the solvent. Otherwise, he's never going to get onto the column to begin with. So he's got to be at least a little polar, right? B has to be at least a little polar in order for him to get into the solution to begin with. And so, he's going to interact with the stationary phase more than he interacts with the mobile phase. And so it's going to take him forever and a day to end up getting off this column. And that's why his peak is way out there at the end. Oops. That's why his peak is way out here. But let's say that, at 6 minutes, as A is pretty much out of the instrument, we start moving what the mobile phase is. We start changing what that mobile phase is from something very polar, say methanol, to something that's a little more non-polar, like acetonitrile or octanol or something, right? Something that still has a little bit of a polar stuff, but that's much less polar than whatever we started with. What's going to happen is that A is going to come out about the same time, and we haven't really affected A because we started with a polar solvent, but because we switched to a non-polar solvent, B is going to come out a whole lot faster than it did before. this particular example is about shortening that distance and keeping your runs to a manageable length. But you could have, let's say that this B peak was really two different things, right? Two different things that are both pretty nonpolar, but because they're both nonpolar, they interact with the solvent about the same. Well, we could set it to where, so wait a minute, let me do this. I'm going to say polar is here, nonpolar up top, right? And over time, let's say we start polar, we could move up to sort of a mixture of the two and just hang out there for a while, right? There's nothing that tells us that we have to go immediately to the nonpolar thing. And then we could move up to nonpolar for the last little bit, right? We can change what the polarity of our mobile phase is pretty much as we want to, right? As long as we have solvents enough to mix together, the HPLC we have can mix up to 4 different solvents, right? And so you can imagine that you can pretty well fine tune what the polarity is. We call that an elution, the elution factor. It essentially talks about the polarity of our solvent, of the polarity of our mobile phase. But you can change this over time and change how quickly things come off the column. All right, so we've talked a good bit about mobile phase and sort of what we do with it. We've talked about, actually interpreting a chromatogram. And so moving into what our actual stationary phase looks like, we have, so the basic terms are normal phase and reversed phase. Stationary phases. This is for separation based on polarity only, right? Based on hydrophobicity. And so normal is only normal because that's what they started with in the 1930s when this really became industrialized. And so they started with polar stationary phase. And a nonpolar mobile phase. Now they started here because the kinds of materials that they could get to pack their columns with were polar materials, right? They started with aluminum oxide, Al2O3. And that was a material that they could manufacture in this very fine powder that had kind of a nice shape to it. And so it packed pretty well. And so that's sort of the first material that they could make these columns out of. And turns out it was polar. And so they could separate nonpolar stuff pretty well. And so things like dyes, colorants that have these big, benzene rings on it and stuff that's pretty nonpolar, they could separate those pretty well. Again, that's where the name chromatography comes from. But over time, and especially in the 70s and 80s, starting to think about pharmaceutical manufacturing, and we're really interested in the things that are mostly polar rather than the things that are mostly nonpolar. What would happen if we just switched this up, right? And so reverse phase, of course, is exactly the opposite. We've got a nonpolar stationary phase and a polar mobile phase. Here I'll put that this was Al2O3. This is usually a C8 or a C18 chains. So here they've got sort of this solid chunk of bead, and these really are still mostly made out of alumina or something similar. but what they've done is they've functionalized that surface. And so now there's a C18, so 18 carbons in a row, right? Of course, with all the hydrogens necessary to give carbon 4 bonds each. But they've functionalized the surface so that now what the mobile phase sees and what the analyte in the mobile phase see are not that aluminum oxide surface, but that C18 non-polar surface. And that's really what they interact with. Okay. Again, these days, this is way more common. This is way more normal than normal phase chromatography, only because most of what we're interested in these days is polar, be it biological for pharmaceuticals and protein folks, be it forensic stuff, usually we're looking at bodily fluids or something like that. It's pretty rare for us to put in a polar stationary phase these days. Okay. And so for both of these, these are both driven by polarity. Okay. And that is by far the most common, this is called affinity, sorry, not affinity. Word has left me. But the reverse phase chromatography is by far the most common chromatography that's run today. Has anybody ever run a manual column in organic? Like you packed a column with the powder and then you put some solvent in it and made it go down. Did you do these this summer, or you did this in organic?
I think Russ and I know the struggle. Those things. Yeah. Oh, I don't miss it.
What did you use as your stationary phase in that chromatography? Do you remember?
Silica.
Silica gel? Yeah. Yeah, and so silica gel is a pretty polar stationary phase, and it's also a pretty common one to put in if you're doing a hand-packed kind of column. Because a lot of times in organic synthesis, we're synthesizing things that don't dissolve very well in water. And so we're going to separate them out with a non-polar mobile phase so that they dissolve, and then separate them out based on what little polarity they do have. Okay. There is, so, these two phases by far the most common. We can move into, well, that's it. We'll talk about the rest of the stationary phases, and we'll talk about the instrumentation on Monday. Okay. I hope you have a joyous weekend.
Can I ask you a question about the lab again?
Ask me a question, please.
The